over here, my dear faculty friends. Myself, Sudha Agri, Assistant Professor in the Department of Information Technology and Co-Coordinator of this FDP. So today I am going to introduce our speaker. Presently he is working as a Principal Data Scientist Manager, APJ at Microsoft, dealing with real-time data also. Means managing a team of fabulous data scientists across Asia, delivering data science solutions for global customers in manufacturing, automotive, transportation and energy verticals. Let us see his professional grades. He worked in sales, pre-sales, operation, finance and legal in different segments like customer products, software development, networking, system integration, data centers and cloud. He is a well-rounded journalist and now he is visualizing, developing and implementing machine learning models for large enterprises. And his awards are Culture Award in the year 2020 and Microsoft Services Award in the year 2019. Sir, you made all of us proud of your distinguished work in numerous capacities. On behalf of our management, I thank you for providing his gracious presence to join us today to enhance our faculty members in emerging technologies like data science, AI, ChatGPT like that. I would like to cordially invite Dr. Senani Nuri sir to occupy the honorable seat.
Before we go to the next section, any questions or responses to some of the basic concepts introduced? Okay, let me ask a question. What is the difference between chunking and tokenization? Chunking is making pieces, I agree. What is tokenization? Can we not say it is making parts? Token is not making parts. Sir, tokens are characters. They are very similar concepts. That's the reason why I was asking this. See, chunking is used in the context of actual application of large language models. Right? If you take a GPT, ChatGPT, or any GPT model, there is a limit of number of tokens which you can input. Okay? The limit is on tokens, not on text length, not on characters. Okay? Usually the limit is, let's say, 4,000 tokens for some model like ATAL 3.5. Okay? Or DaVinci might have more tokens. If your text is running into 100 pages, it will not fit into the model limit. That is when you divide your input document into parts. That process is called chunking. Let us say that we made one page as one chunk. Very simple. What the model does is, it does not break the text in one page into words. It breaks it down into tokens. What are these tokens? That's almost like a trade secret. They simply say tokens. If you go to ChatGPT or wherever API and try to find out what is the meaning of a token, you will be told that roughly 4 to 6 characters make one token, that's all. But the definition they will not give. Whatever was shown earlier about Peter Piper's whatever, that was one statistical tokenization mechanism. But this tokenization is a proprietary technique used by different players and varies, right? I mean, from tool to tool. The only requirement is that whatever tokenization you followed at the time of training the model, you should follow at the time of inferencing also. That's all. Okay. What is the difference between encoding and embedding?
Human level language to that machine level language, you can say this is an encoding.
Okay. Encoding maybe we can define as something very simple where you have one-to-one relationship. embedding can become complicated, right? As we saw, one word prime can have a 50-dimensional vector. That's an embedding. These are actually choice of words. Encoding is a subset of embedding, right? Technically, even in encoding, we can call it as an embedding. Embedding is simply a representation. When you represent the capital word V with number 86, it is an embedding. Instead of number 86 in decimal system, you can also show it in binary system, right? It is still a representation. Instead of binary digits, you can give 0 volts and 5 volts, right? Where 0 is 0, 5 volts is 1, it is still a representation. But generally we use encoding when it is simple and one-to-one, when you can draw it in a piece of paper and a map. It becomes embedding when the representation is less intuitive. But what is the difference between embedding and transformer? Sir, we effective effort level. Jokes apart, these are complicated parts. That's the reason why I'm spending more time. You saw that when we transformed vector V0 to V1, there was a rotation matrix. All of you do it in M1 or M2 or M3. I don't know how the syllabus is here. But rotation matrices are the first thing we do in linear algebra, right? You multiply a vector in the rotation matrix for theta, it gets rotated. It got transformed. Has the dimensionality of the space changed? No. But the vector is now represented differently. When we represent text through vectors, when the initial representation space is not very meaningful, we use transformers to re-represent in a slightly different space, and suddenly this space becomes more meaningful. To give you the simplest example, when we used this ASCII kind of encoding for king, man, woman and queen, the representation space was not meaningful. What is the relation between 86 for V and 103 for small g? It's arbitrary. There is no, that representation space of 1 to or 0 to 255 or 1 to 256 is completely meaningless. But when Venu showed the representation space of authority, has, tail, etc., that's a meaningful representation space. In a meaningful representation space, you could do algebra on words. If you can do algebra on words, voila, computer understands language. Now you are able to process, right, text, speech, whatever, using this rich representation space. The entire point of transformers is to convert an embedding into a more useful embedding, or into an embedding in a different space, so that it becomes more useful. Right? So I'm repeating all this because most of the time, can anybody tell the name of the paper behind ChatGPT, the fundamental paper, one paper which kind of explains what ChatGPT is? Have you heard of something called attention modeling before? Have you heard of ChatGPT? What is ChatGPT? How is it different from earlier bots?
Generates the answers for the queries.
Generates the answers for the queries. Okay. So this ChatGPT is based on a paper called "Attention is All You Need." There is a seminal paper in 2017 by Google researchers. They wrote a paper called "Attention is All You Need." So attention modeling is at the heart of ChatGPT. When they said attention is all you need, they also said you don't need recurrent networks. You don't need gated recurrent networks. You don't need convolution neural networks. All that you need is attention. But do these terms make sense? Convolutional neural network, recurring neural network, neural network, to some extent. Okay, great. Then I have a job here to do. Thank you. If you knew all of this, I had no work to do. Because all that I'm going to now explain is the fundamentals of attention modeling, so that we know what is the theory behind your ChatGPT, which is so popular, which is widely popular. How are we achieving it? And we will do it in a very simple manner, starting with the evolution of NLP. NLP, we know what it stands for? Natural Language Processing, right? So, in this we will cover encoding again. Sorry for repeating it, because we have two different presentations, there's a bit of overlap. Right? And we look at classical methods, then neural networks, word to doc, word to vec, and recurrent neural networks, and LSTM. I am so thankful because none of these are very familiar. Then I prepared my content well. See, historical development of is that you cannot use computers to deal with text if you cannot represent text as numbers. Very simple, right? Any machine, it cannot handle text. It can only handle numbers. So the first one was represent text as numbers. Then we had a linguistic approach for NLP. In a linguistic approach, we had parts of speech taggers, etc. Right? It's a very young crowd here. You would maybe not even be able to name all the 8 parts of speech in English. So I will not even ask in Telugu or Hindi. Right? Because later in English teaching, they stopped teaching these aspects of grammar completely. But earlier generations, they used to do a book called Brendan Martin English Grammar. So they would know all the 8 parts of speech. And when we tried to use computers to process the text, we started thinking like human beings. Okay, is this a noun? Is this a pronoun? Is this a verb? Is it an adverb? Is it an interrogative, etc., etc. A preposition and so on. We used to tag them. This was a linguistic approach towards NLP. Afterwards, statistical approaches started picking up, and we'll cover some of these statistical approaches during the course of this presentation. The first text encoding was not ASCII, by the way. Okay? The first text encoding was not done for a computer. It was done somewhere in the 1840s. It's called Morse code. This was done for an electric telegraph. And electric telegraph itself could be built because we discovered electromagnetism in around 1830. Once we did that, the first usage of physics was to send messages over long distances. For that, they had to encode messages into signals. And one of the most popular ones is Morse code. What you see on the screen here is the Morse code. 1820 is when we discovered electromagnetism. 1824 is when the first electromagnet was invented. Without an electromagnet, you cannot have a telegraph machine. Then 1837, we had the first electric telegram. And then 1844, an American called Morse invented this Morse code. It was so popular that it is still used, right, with some modifications, especially when you are at sea. If two ships have to communicate, right, you can use Morse code using light, right, using sound, using electric signals. So it really stood the test of time, but this is one of the first encodings we had. And the next major thing we had was what is called the Bodo code. This was used as the official representation of text in all telegrams. Does anybody know what a telegram is? Telegram. It's not the app. No, I'm not talking about the app. Long time back, there were no, what you call telephones are not widely spread. You will get selected for job, come immediately. Then Hero Chiranjeevi will rush to Delhi because he got this very cryptic telegram. Telegram was used for extremely fast relay of messages which were important. And there is a language called telegraphic language because they could not send too much of language. Right? All the telegraphic exchanges depend on this standard which was invented by Bodo. Okay? This happened. Madam?
No, before ASCII and Unicode, I was thinking that.
Unicode is the successor of ASCII. See, ASCII represents only Latin alphabet. But what is the most widely spoken language in the earth? Mandarin. Right? How many characters does Chinese have? Or Mandarin has? I should not even ask the question like that. There are 3 different varieties of Mandarin. I should say simplified Mandarin. There is a Mandarin with 500 characters, there is a Mandarin with 2000 characters, and so on. Or how many languages are spoken in the world? How many? Guess? More than 3,000. Thank you, sir. Any other guesses? Some member. We all live in this world, right? Let us hear a bit about our world. How many languages are spoken on earth? 5,000 exactly? Okay. 5,000. Any other guesses? Okay. Do you know the story of the Tower of Babel? It is in the Old Testament. Okay? Right? So even the time of the Old Testament, we already had multiple languages. So the Tower of Babel is about God said, if all these guys speak the same language, they are going to reach up to heaven. Therefore, create multiple languages. That's how the construction of Tower of Babel gets stopped. Suddenly we are not able to talk with each other, people, right? Then we are not able to lay the bricks properly, get the cement properly, the tower doesn't get constructed. But if we take it as a representation of what is happening, maybe our ability to speak language came about 150,000 years ago. We are able to speak because of the lowering of our larynx. In small babies, they cannot speak because the larynx is at a higher level. When the larynx is at a higher level, they are able to drink milk or whatever while lying down. Once you cross that infancy and the larynx slightly lowers, it is dangerous for us to sleep and try to eat or drink. We should be upright while eating or drinking. But once the larynx lowers, we are able to control the flow of air and have very fine motor control so that we can produce different sounds. Right? We can imitate different sounds. We can vary the pitch. All this has happened because of this one small change in our physiology called lowering of the larynx. In boys, when they attain puberty, they develop an Adam's apple when the larynx lowers further. And once that lowers further, the voice changes. మన తెలుగులో అంటాం గొంతు బొంగురు పోయింది అని. గొంతు బొంగురు పోయింది అంటే ఆ లారింగ్స్ ఇంకా కిందకు వచ్చే వరకు గొంతులో మార్పు వచ్చేసింది. In terms of physics, the frequency of that sound comes down. It becomes a baritone. All this change happened maybe about 150,000 years ago. Before 150,000 years ago, we could not control our speech to speak this language. So in the last 150,000 years roughly, we had thousands of languages. Today there are about 7,000 languages are widely spoken. Now my question for ASCII is, మేము ఇంతమంది 7,000 భాషలు మాట్లాడుతుంటే మీరు వెళ్ళి ఓన్లీ ఆ లాటిన్ ఇస్తే ఎట్లా? అది కూడా 256 లెటర్స్. మరి మా భాషలు కావా? మేము కంప్యూటర్ వాడద్దా? ఎట్లా వాడాలి? That was the question, right? Unicode came to represent all the spoken languages, much bigger, much richer. So the current encoding standard, so to speak, is Unicode. Unfortunately, especially in AP, there are still software which work outside of Unicode. Okay? If it is not in Unicode, it is not portable. If it is Unicode, it is portable. It is a very basic thing I'm talking about, but having worked in this field for long, it still pains me to see that people use non-interoperable standards. See, in engineering education, one of the first things you know is you should follow standards. Unicode is the golden standard to follow for all encoding, and we should follow it to the extent possible. Okay, sorry about this side lecture on languages in Unicode, but you get a sense of the problem, right? Where we are. So in NLP, we had statistical approaches and linguistic approach. Linguistic approach is extremely close to my heart, but I will not spend any time here there because, I mean, if you can study linguistics and look at the linguistic approach NLP, it's a joy by itself, right? Anybody who wants to really do that should look at it. Very rich field, and the contribution of India in this field is immense. But today we will focus more on classical ML methods and neural networks. And I don't know how many of these words are familiar to you. We look at bag of words. We will not cover hidden Markov models. We look at TF, IDF, word embeddings, recurrent neural networks, LSTMs, long short-term memories, transformer models, and attention models. Right? Just one slide on a linguistic approach. Does anybody know Panini? Panini. Have you heard of Panini? Sanskrit grammar. Anybody else? So Panini, people know her as having written one Sanskrit grammar called Ashtadhyayi. Okay? I'm sure nobody has heard of the word Ashtadhyayi, right? You heard. Intermediate second language Sanskrit. So, okay, you didn't come from that world. Now, why am I talking about Sanskrit grammar, Ashtadhyayi in this forum? I'll make one statement today, right? Even today, there is no grammar of any language which is as comprehensive as Ashtadhyayi is. Ashtadhyayi is 75 printed pages. It has 4,000 sutras, principles, and people learn them by heart, right? So, even I know many of the sutras by heart. Vriddhi Radhej, we start off like it is some kind of a prayer. In fact, you also use it within puja, by the way, even today. But these 4,000 sutras, 75 A4 pages, describe the Sanskrit language in such a rich manner that a 2,000 page grammar of English does not come anywhere near that. We have universities writing English grammars for 500 years, 700 years now. Oxford, Cambridge date from 1,000 years ago, right? Even today, English does not have a grammar which is the equivalent of Ashtadhyayi. It has been praised as the monument to human intellect. That means if there is one work that human beings have done which reflects their intellect, there is nothing to match Ashtadhyayi. Such a great work. Okay? And this Ashtadhyayi is the one where all the principles of modern linguistics are embedded. So people think it is grammar, whereas those who study Sanskrit know that it is way beyond grammar. Okay? It's actually called a Vedanga. It is almost like an element of Veda. From Panini we had Soshur, who did his PhD in Shashti Vibhakti. Okay? And he is known as the father of linguistics. From Soshur we have Bloomfield, who has developed the linguistics a lot, and almost a separate track got developed with Noam Chomsky. Noam Chomsky is still alive, a massively influential figure in linguistics. He popularized a concept called universal grammar. Okay? Now, this universal grammar is actually within Panini. In fact, in one way, Panini showed how to write grammar of any language. And there's a very nice practical application. Do you know the film Avatar? Avatar, yes. Bahubali? Much better, right? In Bahubali, there is one artificial language. Have you observed? Kiri. Do you know it's an actual language? It was built from scratch, following the principles laid down by Panini and Ashtadhyayi. This was first done in Avatar, where they made the Nami language with 1,000 words. So Ashtadhyayi is broken down Sanskrit greatly like a periodic element of periodic table of elements in chemistry. There are 2,000 roots, 400 pratyayas or affixes, and 4,000 rules for combination of these elements. 2,000 roots plus 400 affixes. How can they combine? Through 4,000 rules. This is what grammar is for. It's a closed set of rules. Almost using similar stuff, we started developing artificial languages used in films like Avatar. The same was copied in Bahubali by Rajwal. That is the generative power of that one. But because we could analyze language so well, for a long time the principles laid down here were used for linguistics-based NLP. And one of the biggest efforts was Anusarana. This started in 1984 in IIT Kanpur. Professor Rajiv Sandar, then he moved to IIT Hyderabad and also University of Hyderabad. I did my PhD from University of Hyderabad. I am very closely aware of all the Anusaraka attempts. The unfortunate part is some of the best brains of India, because they were in the academic world, because there was no pressure to actually do something, they spent their entire career in trying to translate Hindi to English, and none of you are aware of their work. Individually, these people are great. They are very honest, very sincere in their work. Excellent work was done, but today nobody is aware of the work because results did not come. And the key reason for that is not lack of talent, but lack of purpose. If Venu and I don't do our job properly or don't show results for 3 months, we are out of our job. But if I were a professor If I don't publish for 1 year, 13th month also I get my salary, no problem. If I write a software, it doesn't work, nobody is using it, is my job under pressure? Almost the only reason why this did not pick up was that lack of focus on results, lack of focus on rewards. But linguistic approach has a big history, at least in India. Great minds have worked on it. But ultimately, in the practical world, statistical methods are completely overtaken. But any one of you wants to do research or do any linguistic method-based NLP, we are in the right country. We have a huge, very rich knowledge system required for it. And India is the one which donated the knowledge of linguistics to the entire world. If you want knowledge of linguistics, there's no other place to beat India. But today in the market, nobody talks about linguistics-based models. Sometimes they make a comeback for a different reason. It's a topic for a different day. But this is more about linguistic methods. Let us come to bag of words representation. Now you see that sentences can be represented by vectors. Venu kindly explain to us. We have 2 bags of words and 2 vectors to represent them. Here what we have done is, we have taken a dictionary of the vocabulary and we just made frequency counts. Right? This is simple distribution. Now, how do we generalize the representation space? What do we measure? When I do simply frequency distribution, frequency counts, I don't know what is the sequence, right? See, for example, if you look at the word the, it occurs 2 times in both bags. But when did the first the occur, when did the next the occur? I'm talking about this particular part. Right? And we also have here 2 occurring twice. The sequence information is completely lost in this kind of simplistic representation, right? So, we restate the bag of words in a slightly different manner, wherein each word is now a vector, vertical one. And I'm still using the same space, but now it is one-hot encoding. One-hot encoding. In one-hot encoding, what is that we are trying to do here? We have I swam, walked across the road, bank, etc. here. And if I take the word I, if it is I, it is 1, everything else is 0. In these vectors, there is only one element with the word 1, everything else is 0. That's why it's called one-hot encoding. Wherever it matches, we have the number 1. So if you look at the river, it is there in yellow here. In this kind of representation, if I have to show the data matrix, what we do is we transpose these vectors. There is a transpose operation here, and the same thing gets transposed as this one, and this is my data matrix, which is a collection of the transpose of the particular word vectors or the token vectors. And rest of the presentation we use this kind of color because if you start writing our matrices, it becomes very unwieldy, right? So we will use this representation going forward. This is a matrix with dimensions n by d. Okay? Can anybody say what is n here? If this dimension is n, what does n represent? Number of words. And what does d represent? Here, how many dimensions do we have? 13. In this space, we have only 13 dimensions because we only use a small dictionary of 13 words. See, you have dictionary which is a small one, slightly big one, bigger one. We use a very small dictionary of 13 words. So 13 is a dimension of a dictionary, and that occurs as columns in this particular matrix. So everywhere we use the same n by d matrix. N we'll call it as number of tokens. D we'll call it as number of features. Okay? Feature is nothing but an entry in a dictionary or the equivalent of that. Now I know all of you know neural networks, but I will quickly revise that so that we are talking the same language. Okay? See, classical machine learning is focused on features and engineering those features. We finally aim to construct a sentence called y is equal to, a function called y is equal to f of x. Whatever problem you have, it is finally a y is equal to f of x. Okay? If we want to, let's say, predict whatever, what is the production of some factory tomorrow? Okay, that production tomorrow, it could be maybe we are trying to make pens. The number of pens produced today will be Y. And what is X? X can be multiple features. How many people have attended the company today? Right? What is the weather like? How much of raw material we have? All of them will become X. And finally we solve the equation y is equal to f of x. In matrix form we will take the matrix y and also matrix of x. If we solve it, then we have a predictor built and ready. If it's a linear regressor, it's a very simple equation. If it is a decision tree or something like that, it becomes more complicated to represent. But ultimately, it is all in the form of y is equal to f of x. Now the concept of neural networks was, I don't need my terms in f of x to be meaningful. Here we just gave meaningful things for pen production. Number of employees attended. Let's say a factory is there in Rajan. There are 50 employees. 50 employees can make maybe 50,000 pens. If only 40 employees come, maybe we'll make only 42,000 pens. It might not be linear. Right? This is a meaningful feature. But if I simply say a very meaningless feature, but I can measure it, what happens then? That's what a neural network is. What we've discovered is that mathematically it does not matter whether your individual components of f of x are meaningful. For all that you care, okay, I can count the number of times a bus is passing by a way. Okay, I can count the air pollution and still link it to the production. Any meaningless arbitrary ones. In fact, all these still correspond to physical ones. And we have copied God here. It's not that we have invented ourselves. That's why we call it artificial neural networks. Our brains work like this. Our brains have some very simple things called neurons. Extremely dumb things. They can do only one thing. They take a signal and modify the signal slightly. That's all. And these neurons are connected by something called synapses or synapses. Okay? And electric signal flows through them. Based on this simple network, we are able to do memory, we are able to do math, we are able to do voice control, we are able to do language. Everything we do is based on the small signals flowing through extremely dumb processors called neurons. That's exactly what we do in an artificial neural network. You know, we have some 90 billion neurons and 100 trillion synapses in the human brain. We can't replicate that kind of network. But here what we do is, I'm just taking a small part of the network. If we have this part of the neural network, we have 3 neurons, x112, x12, x12, x13, something is wrong here. And they all go into Y. We have different weights for each of the input. And the input for Y will be simply sigma of weight into the input. Is this visible at the background?
Yes, sir.
If it's not visible, actually I'm trying to locate it, right? So the input A will be simply weight into signal of each of them. And in Y, we do a small transformation of f of A. The simplest transformation is called a perceptron, where they say A is equal to 0 if A is less than or equal to 0. I mean, f of A is 0. So if the signal is 0 or less, output is 0. If it is more than 0, output is equal to input, or 1, whichever we can do. We can make it 1 or also equal to input. This is the simplest one. Can there be any dumber processor than this? It's so easy to build, right? That's what a neuron really is. We can have a slightly different one. This formula looks complicated sigmoid, but it mirrors the input very closely in most of the working range. Only at the extremes, it starts to flatten out. If you take a 45 degree line, the sigmoid, the working part of the output is 45 degree, and near the top and bottom, it slightly flattens out. Okay, not slightly, it starts flattening out rapidly actually. But most of the working range, it will mimic the input. The beauty of a neuron is twofold. One, it is non-linear. The most important requirement. If it were a linear processing, what happens is all your complicated neural networks collapse into simpler networks effectively. Therefore, no learning happens. Second, they are so simple, you can do parallel processing using something called GPUs. graphic processing units, which are not very capable machines, which are very simple ones. Whatever principles are in machine learning, same apply in neural networks. Earlier we used to have this, what we call causative models, wherein we used to determine the relation that every worker can produce 1,000 pens. So much of plastic can produce so much of ink can produce so many refills, and do something called ERP, Enterprise Resource Planning. Okay, you will still see some of those people taking training, doing Oracle Financials, SAP. All these are Enterprise Resource Planning softwares. And their precursors were called MRPs, Material Requirement Planning. What is Material Requirement Planning? What does one pen require? One pen requires so much of ink, so much of plastic, so much of whatever nibs, so many tubes, so many barrels, so many people to put together, so many containers to pack. They explore the requirements and they ensure that in that software, when you're trying to plan for something, all your materials are accordingly planned. We still do that. People still go to Amirpet and learn SAP Finance module, right? Even engineers. But in machine learning, what do? We no longer determine these relationships by hand. We don't ask physicists and engineers to determine how much of plastic will make how many pens. We simply look at data for the last 100 days, feed it into a machine, and then we get the output. Same thing with neurons. Now I'm no longer taking plastic and ink and barrels and all that. I'm saying that I'm arbitrarily defining some very simplistic processors, agents called neurons. I'm asking the machine to find out their weights. The moment we do that, we see that this fellow is as capable as a brain. It starts really doing magical things. But it is the magic of math, not the magic of neuron. It is the magic in weights, not in the neuron. We need to understand that. For a long time, this graph I'll skip now because it's too much time here. How many of you are aware of word to vec? Okay, if you're not aware of word to vec, first and foremost, you should be aware. If you want to do anything in NLP, if you know word to vec, it is sufficient. Right? If you're not aware of this, you must go and do some reading on that, because this is the first major breakthrough in creating a representation space which was semantically meaningful. I don't know if my sentence also made sense to you. What is a representation space which is semantically meaningful? That means we finally could figure out a space where we could do algebra on words. Till word to vec came through, it was very difficult to do the kind of operations Venu was showing, which is king minus man plus woman is equal to queen. This paper came in 2013, a very recent one, comparatively speaking. And this is the first time where we were able to do actual processing on language. Till then, we had a very convoluted way of doing various stuff. Okay, I skipped some of the classical methods, let it be. Let me focus more on word to vec. See, what do we do in word to vec is, our intention is to reduce dimensionality. You remember the one-hot encoding that I showed in bag of words? Right? If I use the abridged Oxford Dictionary or whatever, it will be 1, rest of the values will be 0. Each word will have a dimension of 75,000 by 1 if I use the abridged dictionary. If I use the full dictionary, 5 lakh by 1. Even the full dictionary is actually a cheat code. Okay? If you use the full form of words, it will be actually 25 lakhs and even more. Okay, there is something called morphology in language. We will not get into that right now. So the word to vec initial aim was to reduce dimensionality. Can I reduce this thousands into hundreds? The intuition was, can I write a vector Vn, which is a transformation of the vector Xn, as E into Xn, okay? Where we have a d by k kind of matrix is E into k is our dictionary size, 75,000 or whatever you want, and 75,000 by 1. So matrix multiplication, what is the resulting matrix if you take D into K, K into 1? If you multiply a matrix of D by K with a matrix of K by 1, D by 1. If K is 75,000, D is 300, what have we done in this? We transformed the space of 75,000 dimensions into a space of 300 dimensions. Right? So the first motivation for doing word to vec was, how do I reduce dimensionality? The problem was, I need to find a matrix D by K which will preserve all meaning but will dramatically reduce my dimensions. Okay? And we also wanted a meaningful representation space capturing semantic relationships. A semantic relationship is nothing but a relationship which is based on meaning. Okay? Semantics is opposed to syntax or syntactic. Syntactic is about structure of a sentence. Semantic is about meaning of a word. Vakku yokka arthamu. Semantic relationship means relationship based on meaning. We wanted this representation to be meaningful from the semantic point of view. Therefore, book should come near read. Right? Book should not come near something like hit. Though people also hit with a book. That was the idea. When we say near, in the representation space, in this 300 dimensional space, they should be nearby, whatever is meaningful. And the biggest thing was, while training this model, we don't want any labeling data, because finding labeling data was the biggest problem. So what these researchers did again at Google is, you can take sentences like, I'm reading a book, I'm copying a book, I'm binding a book, I'm closing a book, I'm cleaning a book, right? They said, what happens if I remove the middle word? I am dash a book. Right? Now, the internet is full of sentences like this. You take all the sentences, remove the middle word. Now you have the training data, because you know what the middle word is from the internet. But the model did not know. You can train the model to know that. With this, they could do what is called a continuous bag of words model. Why is it called continuous bag of words model? If they take 5 like this.
After 3 minutes, they may take a break for 10 minutes, then
Yes. Once we finish word to vec, we'll take a break. Okay. I'm sorry, maybe this is getting too heavy. I'll take some feedback from you during the coffee break. It is called a continuous bag of words because I have a sliding window of 5, let's say. In a sentence, the window is the first 5 words, then I slide it to 2 to 6, 3 to 7, and so on. That's why it is a continuous bag of words. I simply remove the middle word. Now, because I have huge training data, they could train a matrix like E. Once you got a matrix E, voila, this is your word to vec model. Every word in the dictionary, remember, this corresponds to one thing here. This dimension K is equal to this. Right? Now, every word in the dictionary could be represented by a vector of 300 values. So, when they further reduce this, we showed the example of glove embeddings, which is the smallest model with 50 values. That means they could reduce all the words in a dictionary to a 50-dimensional space, and while doing so, they also added meaning. How could we add meaning? Because you are training the model to recognize words in a context. So, if you look at the probability, with the book, reading might be having maximum probability, right? If you take all the sentences, that's how we could get a representative space, and once you got a representative space, NLP exploded. Huge improvements. That's why the biggest test is machine translation. After 2014, machine translation started really doing well because of this representation. So much so that I was recently going to Vietnam. I came from Vietnam. There they don't understand English much. So I used to take out my phone, type there and it will translate, Google Translate or Bing Translate. It will translate to Vietnamese and they see and understand. And vice versa. So my wife was doing bargaining in a market there. They don't understand English, she doesn't understand Vietnamese. But both of them on a phone, they type and show, it translates on the fly. How is it possible? because you have now an intelligent and a smart representation of both Vietnamese and English. That was possible because of this kind of better representation. Right? There's a reverse way of doing this, where we take the same sentence, I am reading a book, and change it as you are reading a book, he is reading a book, she is reading a book, they are reading a book, Krishna is reading a book, and so on. Krishna is reading a novel, Krishna is reading a comic, a story book, and so on, right? You take one word called reading and generate words around that. In this model, what do? We give the word in the middle and ask the model to guess surrounding words. This is called the continuous skip gram model. The skip gram can be n gram, 3 gram, 4 gram, 5 gram, etc. In this way, they trained word to vec, and we got the first word to vec model. After that, NLP really exploded. Okay, most of your great applications have resulted after this word to vec was done. Understanding of certain terms, but I have some bad news that going forward, the depth will increase and the pace will increase, right? So I asked you to really, bear that in detail. Even if you can glean out areas where you want to work on going further, or have an inkling of what's happening, I would still see that our purpose has been fulfilled. Okay, let me lighten this by reading one poem from Hindi. This is from one of my favorite poets, Dinkar, Ramdhari Singh Dinkar. He wrote a great book called Rashmi Rathi. Okay, anybody heard of the book Rashmi Rathi? Okay, no familiarity with Hindi literature, much less Hindi poetry. Okay, what about the character Karna from Mahabharata? Dana Karna, yes. This is about Karna. Rashmi Rathi is one who has light as his Ratha. Rashmi is collection of light rays. He is introducing Karna in the first one. जिसके पिता सूर्य थे, माता कुंती, सती कुमारी, उसका पलना हुआ धार पर बहती हुई पिटारी. Pitari is a box. He was left in a box, right? सूत वंश में पला, चकामी रही जननी का क्षीर. He didn't even drink his mother's milk. निकला कर्ण सभी रूपों में, तब भी अद्भुत वीर. Okay, this is great poetry in Hindi if you want to read. Ramdhari Singh Dinkar. And there are also viral videos about Asutosh Rana and all, speaking some lines from the same poem. There's one major thing about Krishna going to the Kaurava Sabha where they try to capture him in chains. So many major actors like Manoj Bajpayee and all, they have recited this. If at all you want to enjoy poetry, I will recommend this. But coming back, if you look at the two words jiske and kar, right? I hope all of you can follow Devanagari script, right? You can read what is written. There are two words in red, jiske and kar. These two are related, right? But if you look at the distance, it's huge. When you're trying to process this kind of a text, one of the challenges we have is, how do I know that this Karna in the last line is the same Karna who was described as jiske? Because we only take in the immediate context or only one token we used to take. Recurrent neural networks or auto-regressive models generally, what they started doing was they started considering word about it. Okay? Now, Venu talked about cricket match earlier, right? Do you know that the scoreboard is the state representation of the match? If you want to know the state of the match, what is one thing which will give you the state of the match? Scoreboard. A snapshot of the scoreboard represents a state. So, when we are doing signal processing, we can call it signal processing also. The signal is nothing but word here. At different points in the network, if you want to know the state, then that state will capture all that went before that. And if we keep on passing this state to the subsequent stages of the network, right, we have what is called a recurrent neural network. So in addition to the input in the neural network you saw, we add an additional variable for capturing the state. That's how we build recurrent neural networks. Once you build recurrent neural networks, what happens is, the weights of your various parameters or the learnable parameters, they start representing this relationships coming from earlier parts of the sequence. That is the beauty of recurrent neural networks. So if you see the representation here, we start with an initial state Z0 and the actual input X1. You have two outputs. You have one output variable Y1 and also a state variable Z1. To the next stage of the network, the next input X2 and also the state information Z1 will become an input. And again you get two outputs. One is the state output, one is the actual output you are interested in. Right? And so on. This is how recurrent neural networks capture earlier information. Now in a recurrent neural network, I'll give a simple example so that you understand how it works. This is the problem of English to Dutch translation. In English, you have a sentence called I am happy. In Dutch, it becomes ik ben gelukkig. Okay? You can understand what is I is ik, am is ben. In fact, am is a modification of the English verb be, being. Not many people realize that. And be in English is ben in Dutch. Okay? Because they're very close languages actually. And happy is gelukkig. So what we do initially is, we feed the sequence I am happy into the first part of neural network, RNNs, and ignore the outputs completely. We are only interested in this state information. When we reach this signal captures whatever this information is there and I am happy. Because we already fed all the three words or tokens into this network. Once we have this, then we call this encoder. Why is it encoded? It has encoded the information embedded in the sentence I am happy or the information of the sentence I am happy into some kind of a matrix. When we say state, in NLP it only means a matrix. Okay? In fact, anywhere we talk about state, we represent it as some kind of a vector or a matrix or a tensor or whatever. Once I have the state, then we give a special token called start or anything. It could be anything, but let's say we take the start. This part is called decoder, wherein again each of your I is fed here, therefore you get ik. Now both state and ik are fed, then you get ben. Both state and ben are fed here, then you get gelukkig. This is how we do a decoder in RNNs. Why is this required? Because this is a very simple sentence, you could have done word to word. I is always ik, am is ben, and so on. But remember that am will change to is. If instead of I am happy, I wrote Velu is happy. Okay? Your B form is now is, it's no longer am, because we are now using third person. If I write in second person, it becomes you are happy. Same verb has now become are. So the form of the verb be depends on the noun which has come before. First person am, third person is, and second person are. Not only that, students are happy. It also depends on the whether the noun is plural or singular. So you need earlier state information to translate this properly. Dutch should have similar rules, right? Because it's a system language of English. No, we don't know what those fonts are, whether it is ben everywhere or not. But that is the reason why you need earlier information. But if you go to Rashmi and want it to be translated to English now, the Jiske and Kadri should match. That machine will know they should match only if we are also feeding that particular state. So this was the design of recurrent neural networks, right? Again, after word to vec, this started becoming more meaningful. Recurrent neural networks were there earlier also, but the simple one-hot encoding of bag of words model, we could only demonstrate toy data sets. Practical applications are difficult. Recurrent neural networks, the problem was that the information captured started attenuating. Okay, it became very weak. See, if I am feeding an entire Shakespeare text, that fellow will not remember at the end who is the Prince of Denmark, right? Do you know who the Prince of Denmark was? Hamlet? Or there is a Hindi movie by Omkar or somebody? No. Not Hamlet was some other movie. Set in Kashmir. Whatever, right? But Again, don't ever study English, nobody to beat that stuff like that. So we'll forget, right? Who's Polonius? So much of text RNA was not able to handle. That's when this new thing called LSTM, a new network architecture is there. This is long short-term memory. Okay. So for very long sequences, they have the problems of, technically we call them vanishing gradients or exploding gradients. Depending on the magnitude of the signal, the gradients can either be infinitesimally small or huge. So that the rest of the network doesn't make any sense when some gradient starts being so influential. So to treat long-range dependencies, this LSTMs were there to improve performance. In fact, LSTMs were very popular. I myself used LSTMs in solving industry problems, etc. Very great by themselves. And the only problem was long-range dependencies still remain problematic even in LSTM, and LSTMs takes long time to train. I remember one project where we start the training today, by tomorrow night only the model will get trained. And we replaced it with a model called Prophet, and Prophet was getting trained in 5 minutes. Okay, we had to develop, train some 5,000, forecasting models. I used LSTM for forecasting, but it was doing very well. Especially LSTM would consider the earlier parts. It kind of replaced the auto-regressive models with a better representation, so to speak. But the problem was training time. Why does it take long? It's a sequential model, as you can understand, right? To solve these problems, that while we have a very innovative network architecture, it is giving good results. The two problems were long-range dependencies were still difficult to model, and sequential processing meant that it could not be trained in parallel. That is when this transformer architecture of what we call attention modeling started. We'll cover in attention modeling. This is the key part of this part, so to speak. What is self-attention? What are the learnable network parameters? What is a multi-head attention? The transformer models, transformer language models, and multi-modal transformers. We'll also have some question and answer left after that. This is the core, so to speak. Hopefully, we have laid the foundation for this. Now, we'll start with self-attention first. When we want to model attention, what we are really looking at is, we want to take the input data matrix X, pass it through a transformation layer, and get some kind of a, what you call, I don't know how to call it, X tilde or X approximate, whatever you want to call it, or X bar to make it very simply, right? And both of them should have the same dimensions. Okay? So, I'm reminding our notation is that this is an n by d matrix, n tokens, d features, and each token is a vector, but we capture the transpose of that here. Xn is a vector, Xn transpose is this. Attention is the measure of influence, right? How one token is able to influence the target token. If we want to really model attention, what should we do? For each of these vectors, Xn, for example, for Xn we want to transform it into Yn, okay? Then we need to ensure that Yn is a sum of all the vector tokens Xn with their respective weights A and M. Why A and M? This is valid only for Yn. We could have Y1, Y2, Y3 for each of corresponding them. All of them need to be influenced by other tokens. So let's give them some weight A, and this summation should give us Y. If we have such a model and we learn what A is, then we are able to model attention. Does it make sense? We said attention is that when we are trying to translate this token, this could be bank, right? The translation depends on other tokens also. If the other token is river, the translation of this should be slightly different. If the other token is cash, it should be different. That's what we saw. How do we ensure that in transforming this token, the influence of other tokens is modeled? By simply formulating it like this. That for each token assign a weight and add up the product of the weight and that particular token. Resulting one should be this. Where in the realm of machine learning, our job is to only formulate the model. It is job of the machine to learn what is ANM. Then these are called the attention weights. You with me till now? Even if you know only matrix multiplication till now, it's very clear. Okay. Now we don't want these weights to be negative. So we don't want saying that he is a very negative person, he will influence negatively, she is a positive person, influence positive. No. We don't want this directionality in influence, we only want the magnitude of influence. Therefore, we put a restriction called it should be greater than or equal to 0. Further, we want relative weights, right? We don't want that something is extremely influential. We want to limit it to the space of 0 to 1 so that relatively we know what is the influence. Or somebody has a scale of 0 to 100, somebody has a scale of 0 to 1000, somebody else has 0 to 1 lakh. We don't know all that. We take 0 to 1 and have one more condition that sum of all the weights should be equal to 1. Then we have what is called a partition of unity or relative weights. This is the simplest way of modeling attention. Taking this, we now start going forward. While this is a great way of modeling, we want a richer representation. Okay? So let me take a movie example. All of you use Netflix or any other streaming service or TikTok. You're all users of recommendation service, right? Depending on what you watch, this service is able to recommend something else to you. You're aware of this. Let us take it as an example. Let us say that whatever you use has some attributes. It has a genre, there's a hero, there's a heroine, there's a director, whatever. All these are attributes of the content you consume. Right? And if we attach a value to it, we can call it the key vector of that particular content. Okay? There is this movie called Avatar. Avatar has so and so genre, it is so and so heroine, K11, K12, K13. This movie, Avatar, V1, it's called a value. This value has this attributes. So we call this a value vector. This is the key vector. Now I am a user. I like science fiction. Right? I like so and so director, so and so heroine, so and so hero. So for me, for each of the same attributes, whatever my values are, I call it a query. Q11, Q12, Q13. If my tastes are captured by the query vector, how should a recommendation engine work? Once we have this, we have 3000 movies in our database, so we have 3000 key vectors. And Venu is one user, I am one user. We have different tastes. I like Chiranjeevi, he likes Sridevi. Okay? We have to now find out which movie should be recommended to whom. How do we do that? What is an intuitive way? Madam? Frequency? Frequently watched. Can we use some mathematical language? Sir? Attributes. Okay, maybe I'll ask on the last bench. If we have a set of query vectors and a set of key vectors, how do you find out the key closest to the query? Okay, I'll rephrase it. There are 3 towns, Kakinada, Rajahmundry, Vizag. What is the city closest to Kakinada amongst these 3? Rajahmundry. Why are we saying that? We measured the distance, shortest distance is closest. If I give you the coordinates of Kakinada in lat long and Rajahmundry in lat long, Vizag in lat long, you understand what is lat long, right? Latitude and longitude. Okay? What is the latitude of Kakinada or longitude of Kakinada? Anybody? You should not ask such questions, right? 82.5 degrees east longitude, Kakinada. That is where Indian Standard Time is measured. Kakinada and Varanasi are the 2 places where Indian Standard Time is true. Okay? Never mind that. If I give the lat longs, you can now write a program to find out the closest city. Right? 3 cities, 3 vectors. Our vector is 2 by 1. Lat, long. So how do you find Cartesian distance? Or should we use Manhattan distance here? Okay, I was talking about two different measures. The distance between two cities, when it is Cartesian, it is like a crow flies. A crow can fly directly from Kakinada to Rajahmundry. But a man cannot fly like that. They have to go by along two roads which are more like at right angles. You come from Kakinada up to whatever that place is, what is it, I'm forgetting now, and then take the national highway to Rajahmundry. Right? This is called a Manhattan distance, where it is along avenues in streets which are at 90 degrees. That means it is x plus y, not root of x square plus y square. But you can find the distance, whichever measure you take. You can take multiple measures are there. There is a Mahalanobis distance and so on and so forth. But you can find the distance between two vectors, whatever the distance metric is, and then you can minimize it. You can program it. Now I'll ask the question again. I have represented all movies as vectors. I have represented a user taste as a vector. Which movie would you recommend to this user? Simple. Rajahmundry is a vector of 2 by 1. This user is a vector of 3 by 1. Distance between two vectors. Whatever is the distance measure. Find distance. Minimum distance is the one which is closest to the taste. You follow me? There's the beauty of math. It applies to everything in the same manner. As it happens, the dot product, okay, or the cosine distance is the best distance measure for similarity. Okay, wherever the cosine product is highest, that is the most similar. So we do what is called a dot product. Do you remember what dot product is? So vaguely it was there in 10th class, we already passed it. Okay, it is just a summation of product of each of the elements in the row with corresponding elements in a column, if it makes any sense. But let's say there is something called dot product. We do the dot product and we can find. Right? So, in a movie recommendation service, we are able to find the closest movie to the taste by comparing the distance between the two vectors. The two vectors representing both movies as well as the taste of the user. Once we know the key, we have to generate the corresponding value. See, once we know that Kakinada is the closest, you don't know this vector is Kakinada. You have to look up at both lookup table and say that corresponds to this movie and therefore you serve this. That is how the recommendation works broadly. There are some more details into that, but you get the idea, right? Now I transform the same here. Think of your input vector xn as the value. Okay? We are now trying to model attention. Then we can construct a key for it, but in the time being, let us take the same vector as its own key. That means I replace this V1 with the same matrix. Okay? Then each of the other tokens may be taken as the queries. Rest of the tokens, if you look at our here, rest of the tokens here, we are talking about Excel here, right? Rest of the tokens can be taken as queries. And we can find this similarity. Okay? Similarity is nothing but this dot product. Dot product is given by taking the transpose of one and multiplying with the other. We denote with the dot. This is not matrix multiplication. This is deriving one element of a matrix using dot product. On this, what we do is, since we now have a similarity measure, we apply the softmax function. I am afraid to discuss what is softmax function. Okay, you please note it down. There is something called softmax function. It will make this smoother and easier to interpret at this stage, that's all. But this is the formula of that function. Once we do that, we can compute A and M as this. There is some math involved there because we don't have a classroom atmosphere and we don't have too much of time. I'm taking, trust me, that this equation will resolve. The moment we compute A and M, what do we have now? Have we modeled attention? Right? For modeling attention, we wanted to know what A and M were, right? We wanted to use machine learning. As it were, by using simple math, we are able to model attention. We are able to get these weights. Once we get these weights, this is what is called modeling attention. if I can represent this in this matrix form, y is equal to softmax of x transpose of x. Why? Because the earlier one, all of this, xn transformed into xn, right? When you aggregate all of that, that becomes x and x transpose here. I am skipping the math because of paucity of time and background and all that stuff. But please trust me on this. The same equation which was yn is equal to sigma of amn xn can be written in the matrix form as y is equal to softmax of x xt of x. You will see that we have not used anything external. X is given to us, and all that we did was take an x, did a transport, did a multiplication, did a softmax, again multiply. Okay, this is even more math. That's why I showed that graphic there. But I'm trying to speak in English so that we don't get into the math part. We'll try to make our representation richer. We'll try to make our equation more complicated so that we have more learnable parameters. The more parameters we learn, the better the model will become. Okay, the more complex the model is, the better it will perform hopefully. Here, when we represent it as softmax of x transpose of x, the attention weights are fixed. But as Venu said, we wanted to vary them with data. We don't want attention to be fixed. Also, each feature in x has equal weight, but we might want to vary. Remember, what is feature? Feature is the word in dictionary. Right? All of them now get equal weights because A and M got fixed. But we might want nouns to carry more weight, verbs to carry even more weight, and articles not to carry much weight. We might want to change the weights of each word as well, right? Both these concerns can be fixed if we write x bar as x into u being some dividing matrix, so that we can expand this equation as softmax of xu, ut, xt, where u will have, the matrix u will have the parameters which can be learned during training. Okay, these are the learnable parameters. We can further split this u into three separate things called keys, values and queries. Then we can write the entire thing as q is equal to x into some weights q, keys k is equal to x into some weights of k, v is equal to x into weights of v, and our attention modeling will be softmax of qk transposed into v. Why is v equal to x? Because v is values, right? That's what we are dealing with anyhow. In essence, if you want to remember, write only one equation from this entire session, this is called modeling attention. When you have three sets of weights for keys, values and queries, and represent your output as the softmax of query into transpose of key, softmax on that, multiply that with values, that's when you have the output. This part is called the head of attention, the softmax QKT. You apply that layer to your values, you get and this is the transformer. Remember, transformer is all about transforming 75,000 features into 300 and making it more meaningful. This kind of transformation, this transformer is based only on attention, because what is the only assumption we did? That all of the tokens x1 to xn have an influence on xn, and from there we simply added some learnable parameters to get it attention modeling here. So in terms of matrix multiplication, x is n by d into d into dk will give us n by dk as a k, right? N into d into d into dk. Even for q it should be dk only, we will get another n into dk. And this q into k transpose is, q is n into dk, kt is now dk into n. When we multiply this 2 we get qkt is nothing but n by n. N is number of tokens. We take that qkt, y is equal to qkt is n by n into value vector is n by d, dv actually. We finally get y as n into dv. Same dimensions as our input. So transformers preserve the shape. They show the input in the same space, but we build some learnable parameters into this. Okay, I just explored it earlier, and it's exactly the same thing. Okay. Some question? So this is the same equation I showed earlier, now in boxes, that's all. Of course, they are not boxes, they are matrices, and that's the notation we use. We also talked about scaling, right? Why do we scale? Do you know what scaling is? It's a multiplication factor, right, madam? See, what happens is when you are doing any training, you want all values to be in similar range. Okay? I'll take back the example of Vietnam. Okay? In Vietnam, you go and ask for a taxi. You will say 100,000 dong. 100,000 dong. Okay? In dollars, I don't know what it is. Half a dollar? Not even half.
300 rupees equal to 1 dong.
1 dong, whatever, right?
Sorry, 300 dongs equal to 1 rupee.
1 rupee. But if you put 100,000 dong and 40 cents US dollars, they are roughly equal. When your model has these kind of imbalanced weights, what happens is the plain math of it makes it much more difficult to train because these dongs have a heavy weight. Therefore, as madam said, we multiply them all so that we bring them on the simple scale. That scale is usually 0 to 1, it did not be. So, whenever you have scale parameters, your training times are faster, training cycles are lower. Therefore, I will not say why we got square root of dk, please trust me on that, again involved math. Okay? But the same equation, y is equal to softmax of q into k transpose, or now k into v or value vector. This is also written as attention of q k v. Attention of queries, keys and values. If I represent it pictorially, our inputs are x of dimensions n to d and weights. This is just a formulation, we don't know the weights here. We initialize them with maybe 0, with other initialization. There are multiple initializations, that's a separate part of this entire story. But we initialize it somehow. Okay? And we feed it to the self-attention layer where we compute q, k and v. Each of them are computed as q is equal to x into w of q, which you have given here. K is w of x into w of k, v is x into w of v. And we get the attention, which is after applying a softmax. So you can actually write an algorithm or a program to do all this. That is what is called your self-attention layer. Okay. Now the same thing, even different pictorial representation. Input is x. 3 weight matrices. What are the 3 weight matrices? This one is a weight matrix for query. W, Q. Initialized by some means. W, K, key, value. Initially these two are multiplied in a what is called a matrix multiplication layer. We multiply Q and K, right? Actually K transpose, but we simply show it as matrix multiplication. Then what do we do to that? We scale it. And then we apply softmax. Okay? With this softmax one, we simply multiply with V. Again, matrix multiplication that gives us Y. Why did we pictorially represent this? These now start representing layers in a neural network. So this is the kind of picture you will commonly see. It is exactly equal to this. The right side and left side represent the same phenomenon. But the left side one is more common. And this entire thing is called single attention head. Attention head is nothing but this entire equation. Or this part is the attention. Softmax of this one. Attention layer into Y will give us the output of that. Now, from single attention head, we go to multi-head attention. Can anybody anticipate what is multi-head attention?
Maybe number of real layers like structure.
Exactly, right? You have done it for with one Q, with one K, with one V. Why can't I assume that Q1, Q2, Q3, Q4, K1, K2, K3, K4? I have more heads. That will become multi-head. See, if we keep things simple, concept simple, right? Easy to do even advanced level stuff quite intuitively. The same thing, I'm representing again. See, the attention layer allows the output vectors to attend to data-dependent patterns of input vectors. This is called attention head. Okay? This attention head learns the composite of multiple patterns. But the patterns may pertain to tense, mood, plurality, and so on and so forth. Therefore, if you want to decompose this composite attention, that means, we talked about it, right? You are reading, okay? Or what was that? No, I am happy. The agreement between noun and verb follows a certain pattern in a certain language. If we build our network with components to learn that hopefully, these different relationships are learned more easily. That's the reason why we want a multi-head. Multiple heads will enable learning multiple data patterns. So what we take is, we take multiple heads, 1 to H, 1, 2, 3, 4 up to H, and any given H of small h is attention of QH, KH and VH. Right? And each head will have its own separate Q, K and V. QH is equal to X into WH of Q. That means we initiate different weights for each head because we want these attentions to be learned separately. Right? Similarly for keys, similarly for values, and we concat all of them. How do we concatenate matrices? See, if you remember H, right? H is head, right? In the matrix form, H looked like this one, right? H is nothing but a matrix. Now we have to combine many of such matrices together. And we, in fact, because we wrote H is equal to attention of that, it will have the dimensions n into dv. H will have the dimensions n into dv. Now let us see how we can concatenate multiple matrices with dimensions n into dv. This is dv, this is n, h1. Okay? Put them side by side. That means same rows but keep on adding more columns. h2 and up to hn. So the dimension will be h, sorry, not n. h into dv. Each one of them is dv. There are x such things, therefore n into h dv is the dimension now. But our output should be n by d. So how do we reduce it back to n by d? By finding another weight matrix which is hdv into d. When we multiply both of them, we get our output again as n by d. dv is the values in your dimensions of a value vector, right? Let us say this is 100. Okay? And I am saying that I want my dv to be d by h. 100 should be matrix d by h. Right? So matrix D might have dimensions of 200 and H might have dimensions of, we take 2x. Then what happens is this also will get into the dimensions of n into d. When you have the same dimensions, you will find in neural networks that stacking layers becomes easier. So typically this dv is taken as equal to d by h or reverse way. Right? H is equal to d by dv. Taking it as d by dv will ensure that we can stack layers easily, and this is how we do a multi-head. Pictorially, now we have multiple self-attentions. All of them get concatenated, they are linearized. What is a linear operation? This is the linearization operation. We bring it back. The concatenate was very broad, we want it small, therefore we multiply by one linearizing matrix and we get whatever we want as the output. So this is the multi-head attention layer. Yes, sir.
Scaling also we will do, sir?
Yes. So when we say self-attention, that self-attention is to be exploited with all of those. Its own Q, its own K, its own V, its own scaling, its own softmax, everything.
Individually we will do.
Yes, concatenate. That's what I represented here, right? We will get attention of QH, KH, VH. Attention itself means softmax of Q KT by square root of dV into V. Okay. Now we go to what are transform layers. I'm skipping here because we're already at 12:30, but we got the main part. There is something called a layer norm. Okay. There is a normalization layer. Again, it does the same thing we talked about scaling, wherein normalization allows us to train our networks faster. At this stage, just know that. But typically, it is we add a layer norm or a pre-norm. Okay, both are possible. The key part is we also add a bypass for residual connections. See, each token might have its own word which is unrelated to anything else. For that, we also don't want to connect everything, but we want to have a bypass layer. And that's how we make one transformer architecture wherein we have a multi-attention, right? These three arrows represent the various heads. There is a bypass layer also we add. That means we send the signal directly to output and do what is called add and norm. After that, we add MLP multi-layer perceptron with one more bypass, have a matrix multiplier to get X bar. Okay. Why do we add these components? Because they add flexibility to the transformer. Okay. It is enhanced by having a multi-layer perceptron. Multi-layer perceptron, take it as a black box right now, but it's a simple neural network layer which makes some small modifications in the input signal. But addition, presence of those parameters allows us to learn a lot of interesting behavior. Then the bypass Z signal again we add, where again we do the normalization of Z. I wish I could go more depth in this, I really want to, but because I see that I'm kind of, we are following it to some extent now, but paucity of time, given that it takes much more time to get into it, I'm stopping here. We go to now transformer language models. Okay. There are three kinds of transformer models we can go. One is, let's take a sentiment analysis. We have a sequence of words. It goes to an encoder, and we have sentiment as the output. This is an encoder model. In a caption generator for images, we give a single vector, image vector, and it goes to a decoder, and we get a sequence of words. First one was sequence of words to one word. Second one vector to sequence of words. That's called a decoder. Third one is translation from sequence to sequence. It has both encoder and decoder. So I just want to quickly cover this decoder transformers. When building transformers, what we do is we get the probability distribution of the ordered sequence of words. That's a joint distribution. What is the probability of all of these tokens? It is a multiplication, this is pi, multiplication of the probabilities of each of those tokens. That's a very simplistic assumption. We need to take the conditional probabilities. That means, here I am taking as if xn is independent of all other x1 to xn, but it is dependent on x1 to xn minus 1. Okay. This is for the joint distribution of probabilities of occurrence of these tokens. And in a decoder, what we do is, given n minus 1 tokens, we want to know its joint distribution. That's how these models are. That's the kind of task we give these models. In the next step, what I do is, from this, I do a sampling and pick up one token. I have already n minus 1 tokens. Now n minus 1 plus 1, n tokens I have. I feed that and I get the joint distribution for n tokens. In this fashion, keep on adding, you can generate text using a decoder mode. This is how GPT works. In every stage of the layer, what we are getting is a joint probability distribution of the tokens. So, there is one more thing called positional encoding. Again, positional encoding is a slight subject by itself, so we will not get into it. But what we really do is, we start with embedding. So the first layer always is embedding, something like word to vec. Then we do positional encoding. Then we go through what is called a masked transformer layer, multiple masked transformer layers, ending with LSMs. Okay. What is LSM? LSM is a linear softmax. That means a linear transformation with parameters shared across tokens followed by a soft max. Think of it as a mathematical operation. The only thing I want to explain here is what is masking. You remember we talked about earlier n minus 1 to n to n plus 1 and so on. When you are decoding, you don't want the next word to be known to the model. That is the key part. That is achieved through this masked transformer layer. If I look at my own sentence, I swam across the river. Okay? When I am at the word I, okay, I should know only I. At swam, I should know only I and swam. At across, I should know only these three, but not the fourth one. So, we need to mask everything beyond the current position. Otherwise, what is the point of generating the probability when you already know what the next token is? The task here was, given I swam across or I swam, we want to know the probabilities of various tokens occurring after that. That was the task in generation. So we should mask it. That's a simple thing. That's called a masking layer. Now, encoder transformers work differently. Here, I take the same sentence, I swam across the river to get to the other bank. But I mask or I hide certain tokens. And the model's task is to be able to guess it. We already see it in word to vec. Something very similar happens. So the model gets trained to encode all this text so that this can be predicted easily. It's a straightforward, feed-forward kind of thing, but again we have the same embedding in these models here going through them. I'm skipping through this, I know that, but the reason for that is we really need to go into more depth to blow up each one of these. When we come to sequence transformers or sequence to sequence transformers, which is what LLMs are, large language models, they have both encoder and decoder with a cross attention. What is a cross attention? If you look at the decoder, it was able to generate, right? I swam across the river, based on earlier input, it was able to generate the next one. In encoder, it was able to take a given one and understand it. But when we are doing something like translation or many tasks require sequence to sequence, we also feed the value token into the output. That is called cross attention. That means if I take the translation task of I am happy to Dutch. While you are generating the Dutch language, you also want to know what is happening in the original English sentence. That's what this connection of cross attention does. Okay, then we have multimodal transformers. Sorry, this is spelling mistake, it should be multimodal DAL. Autocorrect, I didn't correct. The beauty of transformers is that the architecture can be generalized. Okay? That means the input need not be text. The input can be Python code. The input can be C# code. Input can be audio file. Input can be an image file. The same architecture works generally speaking. Only tokenization becomes different. How do you tokenize that? Okay? And if I take a figure of cat, right? A pixel is too small a token, but I can divide it into some patches. This tokenization itself, as I said earlier, is a proprietary thing. People don't reveal that. But once we are able to do that, rest of it is exactly the same. Okay. With this, we come to the end of fundamentals of attention modeling. I hope you at least got the gist of how attention is modeled and what is the theoretical framework for that. Any questions? Okay, I have a googly for you. Since you don't have questions for me, I have questions for you. In these two figures, what is the single-headed attention? Madam, you can pass that mic. We have two figures here. Out of these two, which is the single-head attention? Left one. So thank you, sir. You are disbarred from answering any other question for a while now. Because that is right. Do you know why the left one is single-head attention? Apart from that.
Because only one lane.
Only one Q, one K, one B is there. Whereas here, we have many behind it. It is not some kind of a mistake. They are representing multiple layers, one behind another. They are all multiple heads. Okay? Second question. Sir, you are no debate, you know that, right? You are masked. What are the mat-mul operations? In this, we have various things called mat-mul. Matrix multiplication. What are the two matrices being multiplied here? T. What are the matrices being multiplied here? I know, I'm getting pass marks. Okay. Before or after NYD? After the NYD. Before? Into H. Because there are so many heads. All of them are stacked next to each other. Great. You can understand the entire topic very easily. Next set of questions. In this diagram, what is the encoder and what is the decoder? All earlier masks removed. Huh? Sir, zoom there. Zoom on the picture. No, not like that. There is a zoom thing there.
Open magnifier.
Put it on the top of this. Yes. Then keep going up and down. This is the figure. The question is, what is the encoder, what is the decoder in this? What is encoder? What is the decoder?
Left is encoder.
Left is encoder, right?
Because it is encoding the input and then that embedding all the value.
But I have encoders both here, no? There is positional encoding here and also positional encoding here.
So not
we are getting output from the.
that is just to mention the position of the token. But the encoding is like when you are encoding, you are not generating anything from the left side. You are using the output of the.
Exactly, because you get the original paper, okay. Your key is here. In a decoder, you need to mask. Why?
Because it doesn't know the
It doesn't know the next word. There's also right shift there, okay? So the second question is very well.
Yeah. What is it?
Okay, what is the difference between multi-head attention and masked multi-head attention?
In mask multi-head attention, the next stage should not be known.
Perfect, madam. You understand, right? Difference between multi-head attention and masked multi-head attention? Final question. In this diagram, where is the cross connection, cross attention? Cross attention.
Multi-hydration.
Is there no sir? Right side?
Right side and not.
Multi-head attention, right side is there. Where is cross attention? This one.
Yes, sir.
No, this is not cross attention.
Input embedding, not
Input embedding, this is the cross attention. This slide. Exactly, this is the cross attention, right? Because we want also the information from the input embedding to be passed on to the output one. That's how we achieve it through having a cross connection. Fantastic. By the way, the question paper was not an easy paper. Okay, this is a tough quiz question. Correct? Can you tell from where these figures are?
Okay, original paper.
Original paper mean?
Attention is all you need.
Attention is all you need. Did you understand it the first time you read?
Partially.
Difficult.
Yeah.
Did you understand it better now? Is this group understanding it better? That's a great achievement. Exactly, right? This paper was very difficult to read. Attention is all you need. Everybody knew the paper, nobody understood it. I have taken figures only from there directly. You are able to decode the figures. If you know those figures, the rest of English is very easy. You are now ready to go and read the seminal paper behind the current AI revolution called ChatGPT. Congratulations, all of you. Okay, this is slightly more difficult. The question is only one, it's called explain. So this is sentence. The sentence is, in this spirit, left again. It is in this spirit, a majority of American governments have passed new laws since 2019, making the registration or voting process more difficult. UIs and pads are end of sentence and padding, okay, to handle sentences of different sizes. So there is a sentence, and just like I swam across the river, you saw the original attention modeling, where river and swim had some extra weights. What are we showing here? Self-attention weights, right? For making, the maximum weights are towards more difficult, and also end of sentence as it were. Okay, and slightly to 2009. But the interesting part is these colors. You can see some multiple colors here: purple, pink, various colors, right? So you can scroll up or show the part below. Sorry, scroll down. All these show the different heads. We only focused on these attention weights here, but these are composite weights and different. This can be split up into these kind of different heads. That's what this paper shows. Because it's a multi-head attention whatever. Okay. I think I'm giving myself 60 out of 100 in this quiz. Fair assessment, madam, principal, madam. Okay, sir, where do your applications? But before he comes, any questions? Happy to take. We have left out a lot of other parameters like how do we train our own LLM, how many parameters are needed, what is your budget going to look like, etc. But these are interesting questions by themselves because since I'm talking about an academic institution, there is a need for applied research which is relevant to India. And that's really missing because at one level we don't have fundamental understanding very clearly, but where we have, we need to also translate this into a workable proposal. I'm not saying we don't have funds, right? But we need full details, and with that there's enough money floating in the system. But anybody interested to work jointly or whatever, we are more than happy. But I feel the need of the hour is to apply some of this research which is relevant to India. Right? Because we have multiple languages, 23 scheduled 8 languages and so on and so forth, and we need our own NLP tools in India. That I give it to Venu.
Hello, can you hear me?
These are really from signal processing.